Hello and welcome to this video tutorial. Today we are going to simulate a controlled three-phase bridge rectifier using Ansys Twin Builder. In the previous videos I showed you how to simulate an uncontrolled bridge rectifier. In this case we are going to just replace the diodes with thyristor so that we have the controlled bridge. Now to control the controlled bridges we will also need to add the generator, the gate pulse generator using state machines. I already prepared the simulation here and let's discuss each part separately. On the left side we have, for the characterization of the thyristors, we have taken an equivalent line characteristics where we can define, for example, the forward voltage, the bulk resistance and reverse resistance, etc. And then to specify them in thyristor components, I just double click on thyristor and specify, for example, the name of the block, thyristor char.val, in which case it will read all the values specified in the block. I assume the holding current of all the thyristors to be 0 amperes. And I also take a control signal of the thyristor as 1. This is for thyristor number 1. Now if we take 5 more thyristor and arrange them like on the upper bridges, thyristor 1, 3, 5, and on the lower arms, thyristor 4, 6, 2, then we get the arrangement of so-called natural conduction sequence, which are shown here, 6, 1, 1, 2, 2, 3, and so forth. The variables of the simulation I have taken as reference as, for example, inside these initialization block parameters, we took the connection voltage to be 1 kilovolt, line-to-line RMS. The frequency of the grid is 50 Hz. I consider the grid resistance to be 1 milliohms and the grid inductance to be 1 microhenries. On the DC side, I took the inductance to be 50 millihenries and a resistive part of 10 ohms. I also have taken the Simplorer inbuilt variables T-end, H-min, and H-max so that I can have a better control of the simulation performance. Now T-end is the simulation stop time, so to speak. H-min is the minimum time step. I have taken 1 micro, and the maximum time step is taken to be 10 microhenries. I'll show you later where we can change these values in the analysis setup. Now to define the sources here, we have the voltage source where we take time-controlled sinusoidal wave. And here you see I take RMS value to the VRMS, which was line-to-line RMS of the connection voltage, divided by square root of 3. Now, the division by square root of 3 is resulting because we have here a single phase source and we define VRMS to be for 3-phase. That's the reason. And frequency we have already defined for 50 Hz. And it's periodic. For the first phase, or phase A, so to speak, we have no phase delay. Similar for phase B, we have the only difference that it's with minus 120 degrees of phase shift. And for phase C, it's minus 240 degrees of phase shift, or 120 degrees. Now if we go inside each resistive part here on the grid side, you see I have the variable as our grid as defined in ICF block. Same for all 3 phases, and the inductance is also L grid, representing the grid inductance. Now these values are taken as dummy variables. They can vary depending on the design, of course. There may be a transformer before the converter, maybe a current limiting choke, etc. I also wanted to measure the line-to-line voltages. So I added a voltmeter between two lines here, between lines AB, between lines BC and CA. I also wanted to measure the line to neutral voltages, so I connect voltmeters between lines and ground. The circuitry here, we took the control variable S1 for thyristor 1. Let me show you again S1 here. And similarly, I took all the remaining variables from, for example, S1 for thyristor 1, S3 for thyristor 3, and so forth. I took an ammeter here so that I can measure the DC current directly, and a voltmeter to measure the DC side voltage. Inside the load resistance, we have the variable RDC, and for the inductance, we have the variable LDC. Now, it's also important to initialize the initial current of the inductor, which is 0 ampere. Now, let's concentrate on the pulse generator. Now you see I have taken the state machines to generate the pulses of the thyristor gates. Now the state machines are quite powerful to simulate such type of phenomenon. Now to take the state machines, you just go inside basic element states, and here you can choose, for example, drag and drop here. And for controlling the gates of thyristor, the scheme is this one, which is the thyristor conduction sequence based on the natural commutation. Now, if you take, for example, the sequence starting from 6, and then it goes like 6, 1, then 1, 2, 2, 3, 3, 4, and so forth. Now, 6 means the thyristor number 6, and 1 is conducting in this region. And then in the second phase, thyristor 1 and 2 are conducting, and third phase, thyristor 2 and 3 are conducting, and then it repeats. So for that, I have initialized some variables like here. So we have a period of 20 milliseconds. I will take a firing angle, for example, at the beginning to be 30. Then we can change them later, for example, by double-clicking here. Now, to define variables, I discussed in one of my previous videos how to define them. You write the name of variable and then colon equal is equal to the value of the variable. I took an intermediate variable subperiod, which is 1/6 of the period, and then calculate the delay, for example, where I take the reference at the beginning, which is 30 degrees, 1.66, a millisecond, where two line voltages cross, and then we have alpha. This is the total delay. So let's concentrate here on the state machines. So if I click here, you can say, since we will be following this sequence, 6, 1, 1, 2, and so forth. So I set the variable S6, which is the gate signal for thyristor 6, is equal to 1, and set another variable t next to be equal to delay. Now, it's the same procedure. You can click here and add as many variables as you want. By default, you would see if you click on action, it is set to be set. Now, there are, of course, tab, calculation, cati, delete, res. By default, it's set as set, but if you need to use any other parameters, then you will know. You can also consult the user guide for Ansys Twin Builder to have better understanding of them. But for me, I take set. So since the gate pulse of thyristor 6 is set to 1, and we also have a transition here. Now the transition is the condition. When this condition is satisfied, the state machine goes to the next state machine. So this is the condition. It's a if-else, so to speak, in programming language. So time is also an inbuilt variable in TwinBuilder. So if time is greater or equal than the set delay, the thyristor 1 is going to be set to 1. So you see, in these two state machines with one transition, we have implemented, so to speak, this part 6, 1. So in this part, thyristors 6 and 1 are conducting. Now, if I take the time greater than, now from this time, from this state, if the time is now greater than t next, is it t next? In the previous state was defined to be t next plus sub period. So it's every sub period we are adding t next. So we're going to the next phase, so to speak. Now if time is greater than t next, and then we activate, if we consider here 6, 1, then 1, 2. So 1 would be conducting, 1 is already conducting. Then in the next state, it should be 2, thyristor 2. So S2 is set to 1. Now we also need to set S6 to 0 because each thyristor should be conducting for 120 degrees. And if you see from here to here, it's already 120 degrees. So after 120 degrees of conduction period, we set it to 0. Again, the condition of time here is set to time greater than t next. Now at each step, we need to set t next is equal to t next plus sub period. When this condition is satisfied, we go to the next step. Since here it's 2 was already conducting, we need to go to thyristor 3, which is S3 is equal to 1. And since S1 has already conducting for 120 degrees, we set S1 to 0. So in the last phase, thyristor 6 is equal to 1 and 4 is equal to 0. And then it continues and comes to the beginning. Now this is quite crucial at the beginning. For example, you need to define a state with active situation. So you need to start the simulation somewhere. Otherwise, it doesn't know where to start from. So we need to come to the beginning and set the simulation software where to start from. So I said, okay, start from here. So if we go to save it. Now if you activate it, for example, if I if you activate it, and you see a blue dot. Now you see, for our case, the blue dot is here because it was run already and the simulation, when it was finished, it stayed there. But normally when you activate a state, for example, not activated, the blue dot is gone. If we now activate it, the blue dot is back. That means the blue dot is actually here if you're at the beginning of the simulation. After constructing the topology, we need to go to the analysis and add a transient simulation. Now see, by default, the end time, t end, is 40 milliseconds. Minimum time step, which is h min, is 10 microseconds. And h max is the maximum time step, 1 millisecond. Now what happens if I initialize them as variables here? These values are going to override the existing default values. So for example, if we need more accuracy, we can just specify here and the default values are going to be overwritten. To run the simulation, let's go to the Analyze section, click it. If everything goes well, yeah, we have the simulation without any error. Let me show you again. If I rerun it, you will see the blue dot will start actually from here where we activated it first. See shortly. Yeah, it starts here and then it continues. And at the end of the simulation, it stays in this state graph. Now let's go to the results sections and see the line-to-line voltages here. And to have a quick check, I will take two markers. X marker. I will set here the red. I'll take the red as a reference, for example, and take here. So it's 2 periods, or no, 1 period of red. So you see from here to here, it's 20. It's 20, so it's 20 milliseconds. All right, so in this 20 milliseconds, if we set the simulation correct, we should be able to see 1 kilovolt. So to see that, I go to trace characteristics, all, and select the RMS. And in the value section, I'll take X marker range, add characteristics. So you see we have 0.999, so it's 1 kilovolt line-to-line voltages. Now let's go to the line to neutral voltages. In that case, it would be a line-to-line voltages divided by square root of 3. Here we also have the DC side voltage here. This one. If we go back to the schematic, we'll see we have an alpha of 30 degrees. And if we go to line to neutral voltages, take again two X markers. So I will set one at the cross point, which is 1.67 milliseconds, and the other where the thyristor gets turned on, first one, which is exactly at 1.66 milliseconds. So the alpha is 30 degrees. I mean here in this section, from here to here, it is exactly 1.66 milliseconds. Now what if I change the value of alpha, for example? Say I take 60 degrees and rerun the simulation. Now our reference point is still this one, but you see alpha is now 60 degrees, which is 3.3 milliseconds. Let's go back to the previous angle. 30, rerun. Now here are some formulas. If we want to find out the DC voltage, we can multiply the line-to-line voltage with 1.35 and cosinus of alpha. For the DC current in steady state, it should be the DC voltage divided by the resistance only. And for the line current in RMS, we would see the DC current multiplied by a factor of 0.82. Let's go to DC voltage and current. Again, take two X markers. Set 50. So on the left, we have the DC current, and on the right, we have the DC voltage. So the green is the voltage, red is the current. To measure the DC levels of the currents and voltage, we go again to trace characteristics, all, and go take the average and say for X markers in this range. So we have a voltage level of 1.16 kilovolts. Let's calculate the level of voltage. Calculator. So it's 1.35 times 1000 times 30 of cosinus of 30 equal to, so this is 1169, so it's 1.16 kilovolts, so to speak. So it is 1.16 kilovolt, and if we have the current level, it is the voltage divided by 10. Let's go back to see the level of resistor. Our DC was 10. So the current is 116 amperes. Optical calculation is also correct. Now the thyristor currents here we have shown. Now if you remember the sequence of natural commutation, in the first it should be thyristor 6 and 1 conducting, right? So thyristor 1 is conducting where the cursor is, and 6 is conducting. And then if you go to the next section, we see it is thyristor 1 and 2 are conducting, and then thyristor 2 and 3, then 3 and 4, and so forth. So at any given time, 2 thyristors are conducting at the same time. If we consider all the thyristor currents on top of one another, we would see the DC current is built up, as shown on the bottom figure. Let's also consider the line currents. Go to results, create standard report, rectangular plot. Let's take line 1 current, new report. If we calculate the RMS value of it, for that we will need 2 X markers. Let's calculate it for 1 period. Trace characteristics, all, and we will select the RMS. You see it is 95 amperes approximately, and our DC current was 116.8. So if we take 0.82 times 116, it's around 95 amperes.